Hi everyone. In this screencast, I'm going to be talking about the melting points of ionic compounds because we want to be able to explain why some ionic compounds have higher melting points than others. When we're comparing the melting points of ionic substances and we want to predict which one will have a higher melting point, we want to know something about the strength of the bonds in those substances. Remember, for ionic compounds, they exist in a crystal lattice, and the more tightly the atoms in that lattice are bonded together, the higher melting point they will have. Remember, to melt something, I need to get the atoms vibrating fast enough to break the bonds. And if the bonds are stronger, I'm going to need more energy to break those bonds. And to compare melting points, we have to compare a property called the lattice energy of the compounds. The lattice energy of ionic compounds refers to how much energy is required to move the ions from an ionic solid into a gaseous state and break the bonds completely. So that means that if I were trying to calculate the lattice energy of salt, I would take some sample of solid salt and I would heat it up. And I would heat it up first until it became liquid salt, and then I would keep heating it up until it actually became gaseous salt. So I'd have to get it really hot. But if I did this, I could calculate exactly how much energy was required to take it from a solid to a gas, and then I could calculate the exact lattice energy of the salt that I vaporized. The relationship between lattice energy and melting point is direct. Remember, for direct relationships, it means that when one variable increases, the other increases. So the higher the lattice energy of a compound, the more energy I need to take it from solid to liquid to gas, and that means the higher the melting point. And this can be explained with Coulomb's law. In this equation, just like we worked with last time, K is a constant, it never changes, so we can ignore it. Now, the force of attraction can be equated with the lattice energy. Because, remember, the stronger the force of attraction between our atoms, the higher the lattice energy. So here, the higher the force of attraction gets, the more the lattice energy goes up. So we're going to equate force of attraction with our lattice energy. Last unit, Q1 and Q2 were the charge of the nucleus and the charge of an electron. Now they're the charge of our ions. Remember, we're talking about ionic compounds made of cations and anions. And Q1 and Q2 are their actual charges. So if it's a +1 anion, Q1 would be +1. If it's a -2 anion, Q1 would be -2. So there are the actual charges. And then R is the distance between the charges. And the larger your atoms are, the greater that distance gets. Okay? And that's what this note that is cut off down here says. Okay? And again, this is what we're talking about. We're talking about two charges, some cation and some anion, and they're some distance apart. And the closer together they get, the more the force of attraction goes up. And the more strongly charged they are, the more the force of attraction goes up. And we should be able to, once again, use Coulomb's law to realize that the higher the charge, as I just said, the greater the force of attraction, and therefore the greater the lattice energy. Because this is a direct relationship, right? When this number gets larger, my force of attraction gets larger, because this is in the numerator of a fraction. Whereas when my radius of my atoms gets larger, or my distance between them gets larger, then we're going to have a different relationship. It's an inverse relationship, because the size of my atoms is in the denominator. So when I have a larger number here, my force of attraction goes down, and that's an inverse relationship. These relationships will let us predict the melting point of various substances. So if we compare two substances, sodium fluoride and magnesium oxide, we should be able to determine which one will have the higher melting point. For these examples, if you have a periodic table, you should see that sodium and magnesium are right next to each other on the periodic table. So a sodium ion and a magnesium ion have the same electron configuration. That means they're isoelectronic. which will be nice for our example, because it means they're about the same size. For oxygen and fluorine, they're also right next to each other on the periodic table, and their ions are also isoelectronic with each other, meaning that their ions will be about the same size. Okay, so how do we compare the melting points of these substances? Well, let's draw them. I just said that the sodium ion, which has 10 electrons, I'm not going to draw the electrons, I'm just going to draw its 2 energy levels, is about the same size as the magnesium ion, which has a charge of +2. The sodium is just +1. Okay, so these ions are about the same size. Now, these ions are bonded to anions. Sodium is bonded to fluoride, which is also about the same size as oxygen. Okay, so now we want to be able to use Coulomb's law to predict the force of attraction in these two substances. Remember, they're ionic, so I've only drawn 2 atoms here, but they actually exist in a crystal lattice where there's lots of atoms in that 3D structure. But just looking at these 2 atoms, we can still predict the strength of the bond. So, first, let's consider the distance between my charges. My charges are centered at the nucleus. So if I look at my substance on the left, my charge is centered there, and my substance on the right, my charge is centered there. And again, over here, for magnesium, which is +2, that charge is centered on the nucleus, and oxygen, which is -2, that's centered on the nucleus. The distance between the charges can be thought of as the distance between their centers. So that's this distance, or this distance, and the same thing over here. This is the distance between my magnesium and my oxygen, and this is the distance between my sodium and my fluoride. Because my ions are the same size in this case, the distance between them is pretty much identical. So considering Coulomb's law, that variable in the bottom, my R variable, this is staying the same as I compare sodium fluoride and magnesium oxide. But what's different is the actual magnitude of their charge. For sodium fluoride, Q1 would be 1 and Q2 would be 1, because it's actually the absolute value of the charge. And for magnesium oxide, now I'd have a charge of +2 and of -2. So instead of having 1 times 1 in my numerator, I have 2 times 2, which would give me a larger value in my numerator, and means that my force of attraction for magnesium oxide is greater. The distance between them is the same as sodium fluoride, but they're more strongly charged. So therefore, with a greater force of attraction, I would need more energy to break apart magnesium oxide and to melt it. And so magnesium oxide should have a higher melting point. Okay, let's look at one more example. In this example, my distance between the ions was the same, but my charge was changing. In this next example, it's going to be the opposite. So now we're going to compare 4 substances that have the same charges, but that have different distances between each other, because the cations have different radii. All right, so let's take a look at this. I've got 4 substances here: lithium fluoride, sodium fluoride, potassium fluoride, and rubidium fluoride. And just like last time, I want to compare their melting points. Now, if I look at my periodic table, I should see that lithium, sodium, potassium, and rubidium are all in the same group. So they're all going to form +1 anions, but we learned that their radii are going to be different last unit. Lithium is tiny. Okay, it has 1 energy level. Sodium's a little bigger. It has 2 energy levels. Let's see, I'll draw potassium here. Potassium is larger than sodium. It has 3 energy levels, 18 electrons. And then rubidium is my biggest cation in this example. Rubidium is beneath potassium, so it has an additional energy level. It's got 4 energy levels. It's a huge atom. Okay. So now let's compare the actual strength of these bonds by drawing in my cations, just like I did last time. Excuse me, I mean my anions. I already drew my cations. So we're working with fluoride all the way down, so the radius is the same for all of my anions, because it's fluoride every time. Fluoride has 2 energy levels. Okay, and then finally one more fluoride over here. So now, how can I compare the strength of attraction between these ions using Coulomb's law? Well, again, Coulomb's law tells us that the force of attraction is related to the constant times Q1, Q2 over R squared. Now, remember, in this case, they all have the same charge. So my numerator is going to be 1 times 1 in all of these examples. This will be the same for all of these examples. But my distance between my charges is getting greater as I move down the group. Lithium fluoride, those ions are smaller. They're really close together. Sodium fluoride, the distance gets a little larger. Potassium fluoride, a little larger than that. Rubidium fluoride, my distance between my charges is huge. And so, as I move down the group, my distance between the charges gets greater. And because of the inverse relationship with force of attraction, my force of attraction goes down as I move from lithium to sodium to potassium to rubidium, which means that rubidium fluoride should melt really easily. These particles are not very strongly attracted to each other. Whereas lithium fluoride, I have these tiny, tiny particles with charges closer together. There's going to be a strong force of attraction there. And so lithium fluoride should have a really high melting point, but rubidium fluoride should have a really low melting point. Okay. All right, I hope this was helpful, and